Hi, this video is all about kinetic energy. Kinetic energy is any form of energy that arises from an object due to that object's motion. If an object is moving, then it has energy, and that kind of energy we call kinetic energy. The word kinetic means movement or motion. There are many ways that you can move, and so because of that, there are different kinds of kinetic energy. Three common categories are vibrational, rotational, and translational. Vibrational would be things like sound waves or just vibrations, earthquakes, those are things that are moving and vibrating, and that gives them kinetic energy because of that. Rotational kinetic energy is what it sounds like. Things that rotate or spin have rotational kinetic energy. But the last one is the one that we'll focus on most in physics classes, and that's translational kinetic energy. This kind is just moving from one place to another laterally, like left or right, up or down. It's just you're translating the position of an object from one place to another place. And so that's what kind of kinetic energy we're going to be dealing most with. Now, in order to truly understand kinetic energy, to start making sense of our world using kinetic energy, we need a way to measure it. We need a way that we can assign a number to energy in the form of motion. So how might we do that? So to measure how much energy an object has because of its motion, we have to remember that the amount of energy an object has is related to the amount of work that you do on that object. So let's say we have a shopping cart. Okay, that's an easy example, where we push on the shopping cart with some force, and that shopping cart moves some distance, let's say. So it goes from here to here. All right, because of the force that we apply over a distance, we have done work on the shopping cart equal to force times the distance. Now I'm going to use some other equations here that we've probably seen before in our physics study that will allow us to kind of rearrange the work equation to give us an expression that involves energy in the form of motion. So one equation I'm going to use is Newton's second law, which says the net force is equal to the mass times the acceleration. And then another equation I'm going to use is one that involves the speed of an object as it accelerates, and that is the final speed equals the initial speed squared, final speed squared equals the initial speed squared plus 2 times the acceleration times the displacement of the object. I kind of ran off there a little bit. So that equation paired with the Newton's second law equation, we can do some rearranging of this original work equation. And the way that we'll start that is I'm going to take this force right here, and instead of using force, I'm going to use mass times acceleration. So work equals mass times acceleration times delta x. And I'm also going to do some rearranging of the equation over here. I'm going to solve this equation for this quantity, acceleration times delta x. So to do that, I'm going to subtract the initial speed squared from both sides. And so I'll have the final velocity squared minus the initial velocity squared equals 2 times acceleration times delta x. And then I'll need to undo this times 2. I'm going to divide this by 2. Okay, so that will allow me to basically rewrite this final velocity squared minus the initial velocity squared over 2 is equal to acceleration times delta x. Now that might seem odd why I chose to do that, but if you look, I have acceleration times delta x here, and I have acceleration times delta x over here. That allows me to substitute out acceleration delta x, and I'm going to substitute in this part. So let's do that to our work equation. So work is now equal to mass times this big fraction quantity here, the final velocity squared minus the initial velocity squared over 2. So I've done all that so that I can kind of do some rearranging. I'm gonna distribute the mass to both of these quantities, and I'm gonna also separate this fraction a little bit. So I'm gonna just do some algebra here. Work equals mvf squared over 2 minus mvi squared over 2. So I've applied the divided by 2 to each term, and I've distributed the mass to each term. And so just to write it one other way, just to make it a little bit more traditional, I'm going to write it like this, with the 1/2 out in front. So now I have this quantity here, 1/2 times mass times the velocity squared. I have the final velocity minus the initial velocity. So this little 1/2 mv squared has what we wanted in it. It has a speed in it. So the work that you do is related to the change in the speed in this way. So this little quantity of 1/2 times mass times the speed squared, this quantity we're going to call the kinetic energy of the object. And that allows us to say, okay, this is the final kinetic energy and this is the initial kinetic energy. So in other words, the work that you do on this shopping cart is equal to the final kinetic energy minus the initial kinetic energy. This is the final, this is the initial, and final minus initial is the change. So the work that you do on an object equals the change in the kinetic energy of that object. And kinetic energy is, as we defined it, 1/2 mv squared. So this is how you can sort of quantify the energy of a moving object with this quantity right here, 1/2 times mass times velocity squared. That is the kinetic energy of an object. Now, all of that work that we did to come up with an equation for kinetic energy is not necessary for you to understand kinetic energy by itself. It's just helpful to kind of see where kinetic energy comes from. It didn't just, pop into existence. There's a reason why it has this equation here. And so now that we know where it comes from, let's talk about kinetic energy in real scenarios. So kinetic energy is equal to 1/2 times the mass of an object times its speed squared. And based on this equation, kinetic energy has a directly proportional relationship with an object's mass and a quadratic relationship with the object's speed. A quick review of these two mathematical relationships. Directly proportional means as x increases, y increases by the same factor. So an example would be if you double the x quantity, then the y quantity also doubles. If you double the mass of an object, then the kinetic energy also doubles. It's by the same factor. Quadratic, on the other hand, is similar. As x increases, y also increases, so the first line is the same. What's different for quadratic relationships is the y value increases by the square of the factor. So as before, it's by the same factor, now it's by the square. So if you were to double x, then y would increase by a square of doubling. So double is times 2, so 2 squared is 4, so y would increase by a factor of 4. Or if x tripled, then y would increase by a factor of 3 squared. 3 squared is 9, so y would go up by a factor of 9. So this is a quadratic relationship, and that's what we see for kinetic energy and speed. So let's look at some example questions here. Suppose a bowling ball has 24 joules of kinetic energy. How much kinetic energy would the ball have if it, A, had twice as much mass and was moving at the same speed? So we've doubled the mass, the speed does not change. So doubling the mass means we're going to double the kinetic energy. So it would have 48 joules. It's hard to write sideways over here. Okay, so 48 joules of kinetic energy if you double the mass. For part B, what if it had the same mass as it did originally, but was moving at twice the speed. Okay, if we double the speed, like we said before, it's a quadratic relationship. So we're going to take the doubling and we're going to square it. So it'll be times 4. So 24 times 4 would be 96 joules. Okay, what if we had 1/2 the mass, but it was moving at the same speed as originally? So half the mass means, whatever change you do to the mass, it's going to be the same change in the kinetic energy. So it'll be half as much. So that would be 12 joules of kinetic energy there. What if the bowling ball had the same mass and was moving at 1/2 the speed? All right, this could be a little tricky. You got to figure out what would be the square of 1/2. So if you did 1/2 times 1/2, what do you get? Well, half of a half is 1/4. So this would be 1/4 as much kinetic energy. So 24 divided by 4 would be 6 joules. All right, part E, what if it had 1/2 the mass and was moving at 1/2 the speed? So what would happen to the kinetic energy then? Well, it's going to go down. 1/2 the mass caused it to be half as much, but 1/2 the speed caused it to be 1/4 as much. So how do we add those together? Do we just add 1/4 plus 1/2? What we do is we just multiply this number by both of the changes. So we multiply 24 by 1/2, and then we multiply 24 by 1/4 because it's 1/2 squared. So 24 times 1/2 would be 12, and then times 1/4, 12 divided by 4 would be 3 joules. So this hopefully gives you an idea of how changing one variable in the kinetic energy equation has an effect on the kinetic energy of the object overall. So that's all I've got for you in this video. Remember, habit is the battleground of character.